All right, this is AP Calculus ABB, Unit 2, Lesson 7. I thought I would record a video that gets to the root of Simpson's rule. I keep wanting to say Simpson's paradox, that's something else. The Simpson's rule, which is written on the screen. And it was mentioned in the video that it comes from an approximation method using 3 points and fitting a parabola to the 3 points so that you create somewhat of a curved interface or boundary, upper boundary on the function. That doesn't mean it's going to fit the function perfectly, but that it may produce in some cases a more precise example. And in our example in our previous video, it came out to exactly the same, though I'm quite certain that the shape of the parabolas does not match exactly the shape of the function. It's just that the losses and gains canceled each other out and ended up being the same answer. That said, in this video I'm going to get into the roots or the origins of the Simpson's rule a little bit more. So let's set this up this way. I'm going to create a graph for a generic scenario. For simplification purposes, I'm going to center my graph at 0 on the y-axis. Okay, and so I'm going to go to the left a set distance, we'll say negative h, and I'm going to go to the right the same distance, we'll go say positive h. Okay, and we'll get out some function value for h. Then the function value we'll get out we'll call y sub 0, and we'll get out some function value for 0, we'll call that y sub 1, and we'll get out some function value for h, we'll call that y sub 2. Okay, and we'll fit a smooth parabolic curve to this. Okay, now in the way I've drawn it, the vertex of the parabola is going to be somewhere between y0 and y1, but you get the idea. We can fit a parabola to any 3 points. And this function here, we'll call this f of x is ax squared plus bx plus c. Okay, just the generic form for a parabola. And what we're interested in here is the area under the curve. Okay, the area under the curve. And so toward that end, I'm going to take the integral of f of x. And I'm going to integrate. It's the great integrate. I'm going to integrate from negative h to h on f of x, which is ax squared plus bx plus c dx. Okay. All right, and this is going to involve a bit of writing, but hopefully it'll work out here. So the integral of ax squared is ax cubed over 3. So ax cubed over 3. Okay, plus bx squared over 2 plus cx. And we're going to evaluate this from negative h to h. Okay. All right, so let's plug in h. And let's move things over here a little bit. I'm going to rearrange some things. One thing I can do with computers that is difficult to do with paper here. I'm going to move my f of x out of the way. Okay. And let's see here. So we're going to plug in h. So this is h cubed over 3 plus b h squared over 2 plus ch minus quantity. This parentheses is kind of necessary. Negative h cubed. So negative cubed is going to be negative. So this is negative ah cubed over 3, because when you cube a negative, you get a negative. and vh squared, but negative h squared. Negative h squared is positive h squared. So this is going to be plus vh squared over 2. And the signs working out correctly become very important here. And then minus ch. Okay? And now I'm going to distribute the negative sign. So this becomes positive, this becomes negative, this becomes positive. Okay, the vh squareds over 2, you notice, cancel out. Vh squared over 2, minus vh squared over 2. The ah cubed over 3's, there's 2 of them, and there are 2 ch's. So this simplifies to 2, and I'm going to put this over here. This simplifies to 2 ah cubed over 3. 2ah cubed over 3. And then plus 2ch. Okay? And I'm going to get rid of all of these steps, but I wanted you to see them because I don't want to be lost in the woods here, lost in all the details. Okay? But feel free to pause this and write down the steps here. Okay, I'm going to run into that here. Okay, so there's my integral. Let's move things around. Okay, the integral from there. Okay, and I want to rewrite that integral in a different form. Okay, so let's figure this out. I want to figure out what y0, y1, and y2 are in terms of f of x. So y1 or y0 is going to be f of negative h, right? So this is a negative h squared, negative squared is positive, plus b negative h, so minus bh, plus c. Okay, y1 is going to be a f of 0, and that turns out to be c, because the x squared and the x drop out is 0 and get to be 0. All right, y2 is f of h, and f of h is ah squared plus bh plus c. Okay. And now the reason will become apparent here in just a moment. I'm going to combine y0 and y2. So y0 plus y2 is 2 ah's, ah squareds. The bh's drop out, so b drops out, plus the 2c. Okay. Now I'm going to look for that in my integral over here. But in order to see that, I'm going to do something here. I'm going to factor out 3. Now I notice I have an h squared, not an h cubed, so I'm going to factor out an h. Okay, and let's see what happens when we factor out h over 3. So we're left with 2ah squared plus, now a factor of 3 out of 2, think of this as 2 over 1, right? And it's basically, when you factor out and divide 3, it's the same as multiplying by 3. So 2 times 3 is 6c. Okay? That's almost what we've got right here. Okay? Look at that. Almost what we've got right there. I can do a little bit of modification to make it fit here. So equals. Yeah, just equals. So this equals h over 3 times the quantity, 2ah squared plus 2c plus 4c. Okay, now with the little direct substitution here, I can get this. I can get this part right here, this 2ah squared plus 2c. That's y0 plus y2, right? And this C, we've already said y1 is C. y1 is C. So doing a little substitution, we end up with h over 3, okay, y0 plus y2 plus 4y1. And rearranging just a little bit more again, just a little bit more, we now have h over 3 times y0 plus 4y1 plus y2. And that should look very familiar if you look at Simpson's rule up above. Okay? So we just have evaluated, what we've demonstrated is, at least for this case here, that the integral, let me copy, the integral from negative h to h of the quadratic that fits those 3 points, is h over 3 times the quantity y0 plus 4y1 plus y2. Oh. Hold on, need to merge layers here. There we go. Now we should be able to copy and paste if I have the right tool selected. Little technical difficulty here. There we go. Equals. Okay. So that's the integral. That's kind of the surprise result. Now let's generalize it a little bit more. Okay. We can generalize it a little bit more by expanding this. This is just a set of 3 points, right? What if I expand it to a set of 5 points or 7 points? Or this is 2 intervals, 4 intervals, or 6 intervals. Always even numbers. And I hope you remember that Simpson's rule only works for even numbers. Okay? Let's generalize it this way here. Let me move things around and switch colors here. Okay, let's go to blue. All right, so let's say we do this. We have some function that we're going to evaluate for 3 points. And then 3 more points. And then 3 more points. Okay, so this becomes a set of a parabola here, a parabola here, and a parabola here. So we literally have 3 parabolas, right? But we've got actually 2, 4, 6 intervals. Okay, and let's call this y0. I actually call this y0. This y1, this y2, this y3, and this y4, and this y5, and this y6. Okay, then the integral becomes, and let's consider this a and b, and this to be h, right? Then the integral from a to b of f of x dx becomes h over 3, and let me do this down below because I'm going to need some room. Becomes h over 3 times the quantity becomes h over 3 h over 3, there we go, times the quantity y0 plus 4y1 plus y2 plus, right, h over 3, next parabola, y2, because we use that same boundary twice, right, y2 plus 4y3 plus 4y3 plus y4 plus h over 3 y4 plus 4y5 plus y6. Okay. Notice they all have an h over 3, which we can then factor out. H over 3 times. Now there's only one y0. There's a 4y1. There's a y2 here and a y2 here. So there are two y2s. There's 4y3s. There's a y4 and a y4 for two y4s. And then there's a 4y5s. And then there's a y6. And there we have Simpson's rule for n equals 6, right? And you can imagine how it would work. There's always the first and last are always single. There's no multiplier, no coefficient. The second and second to last always have 4, and then all the ones in between that share boundaries have coefficients of 2. Okay, so now hopefully you're not expected to be able to do this derivation, though it would be a good exercise to do so. But hopefully this gives you some understanding for where it comes from, that there is a definite reason or rule for our understanding for why it works the way it does.